Okay, welcome to Chemistry 111. We last left off talking about effective nuclear charge and atomic size. Now, we don't need to know any of the actual math behind it. There is some method to the madness. Effective nuclear charge is how much of the nucleus's positive charge do the valence electrons actually feel. With electrons within a energy level will feel the nucleus about equally. There will be some protection from the valence from the shielding between the orbitals, but it's going to be very slight. But as we move up in energy levels, we're essentially creating a barrier that will protect the outer electrons from the nucleus. The inner electrons will acting as a shield. And the generalized effect is that as we move down the table, down the periodic table, the elements below in the group will have only a slight increase in effective nuclear charge, despite adding anywhere between 8 and 18 new protons. As we move across the table, though, we will see a gradual increase in effective nuclear charge because when we add one proton, the one electron we are also adding does not give a complete shielding. So we're seeing a greater increase moving across the table. Now, how this applies to the atomic radius is that the atomic radius, or the electron cloud, essentially is pulled closer to the nucleus based on how much of the effective nuclear charge the electron cloud feels. When the electrons feel strong nuclear charge, they are pulled tighter and tighter into the nucleus. And that results in seeing a decrease in size as we move from left to right on the periodic table. We see a greater effective nuclear charge, so we see a corresponding decrease in size. As we move down the table, while the effective nuclear charge is going up slightly, the principal energy level is going up. And so we're adding another layer of electrons and another layer of electrons. And this is going to result in an increase in size. Now, we also want to talk about ions. Ions, we use the same concept here, but now we're thinking about what happens. What happens when we add or subtract a negative? Because the nuclear charge will not change. The nuclear charge will not change. The electrons in the cloud will change. So what's going on? Cation is pretty easy. Cation is you remove an electron, so we remove some degree of shielding, and now each electron remaining is going to fill the attraction that much more. When it fills the attraction, it gets pulled in even tighter. So we don't have any of the protection. It's like if you're walking your dogs and one of them breaks through from the leash and you have a friend, you tell your friend how much more tighter you don't want any more of them to get out. Try to watch, make sure there's no more escape. So you get pulled. The opposite is true for an anion. For an anion, when we put an electron in there, the Z effective has stayed the same. But now we have more electrons, which is going to create a greater repulsion, pushing everything out a little bit more. We're adding a little bit more shielding, so everyone's feeling the electronic pull a little bit less, and they start to expand out. So when we add electrons, we're forcing the cloud to get bigger. When we're removing electrons, we're allowing it to shrink in a bit. So cations are always smaller than the nuclear, than the neutral compound, and anions are always bigger than the neutral compound of the same element. And with this in mind, we can actually arrange isoelectronic atoms in increasing size based on their negative charge due to this effect. Electronic means same number of electrons. So just real quick, isoelectronic system, such as neon. Neon has 10 protons, 10 electrons. Fluorine has 9 protons, 10 electrons. Oxygen, 2- would be 8 protons, 10 electrons. Sodium would be 11 protons, sodium plus 10 electrons. And magnesium, 2+, would be 12 protons, 10 electrons. This is a perfectly isoelectronic system, meaning all of these atoms and ions have 10 electrons. The only way they differ is the number of protons. So based on that, which of these guys is the smallest, which of these guys is the biggest? If I arrange these guys based on their size, magnesium is going to be the smallest, oxygen is going to be the biggest, because the more negative it is, the bigger it is. If you want to look at it in terms of protons, the bigger the proton count, the more they can pull them in, the more they can attract those electrons. We got a lot of positives pulling on 10 negatives. This, we have a lot less positives pulling on 10 negatives. And so these guys are able to pull away and spread out that much more. So if we're comparing these guys, this perfectly isoelectronic system, the most negative one is the biggest, the least negative, the most positive is the smallest for an isoelectronic system. But we should be able to compare the sizes of ions pretty easily. Okay, ionization energy. So this is one of the first real trends that deals very heavily with reactivity. Ionization energy is described as the ability to remove an electron from the valence electron shell. And so the more easily this is achieved, the more easy it is to become positive, the more easily it is to make an ionic bond. Physically, it's the energy required to remove an electron in the gaseous state, but it's an energy cost. How much energy does it take to excite an electron from the ground state all the way outside of the atom? How much energy does it take to move it into infinity? So, but this is an energy cost. Now, atoms with low ionization energy do not bind their valence electrons very strong, and thus they're going to be very reactive, which is why you see a video of, say, someone cesium in water, it's going to explode powerfully. It's going to destroy the container because it reacts so readily, it produces a bunch of energy and hydrogen and auto-ignites. But okay, so how do we understand this trend? So we want to look at how the valence electrons are being held. This is going to be a competing trend between size and effective nuclear charge. Remember, effective nuclear charge controlled the size in itself, but here we're looking at, it's not just a direct correlation. Higher Z effective means higher ionization energy. Because as we remember, going down the table, effective nuclear charge went up a bit, but it went up. But size also went up. So the trend actually is that the stronger the electrons are held, the more closely they're held to the nucleus, the harder it is to remove. So remember, the elements on the far right of the table, the elements were smaller and they had a higher Z effective. So not only are they closer to the nucleus, they're also held more tightly. And so those guys are going to be harder to ionize. On the other hand, elements on the left are going to be bigger and have a lower Z effective. So the electrons are going to be further away and the Z effective is going to be smaller. So it's more easy to remove them. It's easier to remove them. Now, as we go down the table, Z effective may go up, but the size of the atom goes up significantly. As we're getting further and further away from the nucleus, we're going from 1s to 2s, 2s to 3s, 3s to 4s. We're getting further and further away from the nucleus. We're getting further away from that positive attractive force. We can pull them away that much better. Like if you had a prison, just for example, prison, and it's a jail, you're going to be able to listeners pretty well. But if you're looking at a jail that's ranging over multiple miles with lots of open space, it's going to be a lot harder to watch everybody. As they get further and further away from like the central guard tower, you can't watch everyone nearly as well. It's easier to pull those electrons away. If you have some dogs, a leash, the longer the leash is, maybe the easier it is for it to break. And even if it does break, less like a chance you'll be able to grab the dog before he gets away. So in general, the elements on the bottom left are going to have the lowest ionization energy. The bottom left elements are going to have the lowest ionization energy. The top right is going to be the highest ionization energy, meaning they're the least likely to go positive. And down here, it's the most likely to go positive, which is why cesium and sodium and potassium and rubidium are always going to be like +1. We tend to look at those at +1 rather than -1 because they have a low ionization energy. It's easier for this to accomplish. Now, there's ionization energy doesn't have to just be one electron. It can be for multiple electrons. Generally speaking, though, what happened when we had a cation? When we lost an electron, what happened? The atom got smaller. So when the atom gets smaller, the remaining electrons become more tightly held. When they become more tightly held, it's harder to remove a second electron. And if we remove a third electron, it's even harder because it's becoming smaller and smaller. However, there is a certain point where we see a huge change, a big, big change. In general, the successive losses should be something like doubling of the first one, or adding one equivalent of the first energy, until we get to the core electrons. And this is because of this. Let's look at this little picture. If I am removing all the electrons in this outer layer, if I'm removing all the electrons out of the outer layer, each time I remove an electron, it gets a little bit smaller, And so it's harder to remove the second one, and harder to remove the third one and fourth one. But when we get to the point of we have to remove this guy, this 9th electron, suddenly we are removing from the next layer. This is super close to the nucleus, as opposed to the second row, which is further away. So when we go from the valence electrons to the core electrons, it's going to shoot up. It's not going to be a simple doubling of energy. This is going to be increasing by like 7 times. So if you look at this, lithium right over here, the first electron is 520. The second electron, which is a core, is 7,000 something. It's jumped from 500 to 7,000. Beryllium, I'm not sure if that's 899. It doesn't really matter. But it's a little bit higher because remember, ionization energy goes up as we go across the table. The next one, 899 or whatever, jumps to like almost 1,800. But then goes from 1,800 or 17 something to 14,000. That's 7, 8, 9 times as much. It's becoming way too hard to lose another electron because we're attacking the core. Boron, gone up a bit, or it's stayed about the same because of the P. Then it goes to 24 something, then 36, and then 25,000. 25,000 is this huge jump as we go from row 2 to row 1. Same thing, carbon, 1,000, 2,000 something, 4,000 something, 6,000 something, 37,000. Carbon can only lose 4 electrons before it becomes too prohibitively costly to remove anymore. Same thing, nitrogen. Nitrogen likes to be negative, so it's getting very costly to remove electrons, but it's still possible. 9,000 jumps to 53. Fluorine, 16, 33, 60 something, 80 something, 11,000, 15,000, 92,000. So you see, this is a jump of about 2 to 4,000 per time. And then it's not just a jump of 2 to 4,000. It's now like, that's just a huge increase, like 8 times, 7 times as much. A huge multiplicative effect as we go from the row 2 to the core, which would be the 1s. So one thing you should be able to do, there is a question on the homework about looking at the ionization energies of an unknown atom. You could pick out what row this atom must be in. Because you'd be looking at, if I saw something that's, 800, 2,400, 3,600, then jumps by a factor of 9 to 10, I know, oh, it can lose 3 electrons, so it must be in 3A or 13. It must have 3 valence electrons. Doesn't matter whether this is boron or aluminum or gallium or indium or what's TL, thallium, is that? It doesn't matter because it's going to have that same general premise. Okay, I'm sorry. Now, the last trend we really need to talk about is electron affinity. Now, if ionization energy is the ability to remove electrons, electron affinity is the ability to add electrons. What is if ionization energy is the energy lost, the energy cost to pull electron out, electron affinity is the energy gained to put electron back in. Now, this trend will actually look to be identical to the ionization energy, but that's just because of the verbiage, because energy lost was highest at the top right. So the energy gained will also be highest in the top right. So in this case, high is good. Previously, high was bad because you want a low cost, high resale. But in this case, top right is going to be high cost but high resale. So as we move left to right, electron affinity will increase. Why is it going to be increasing? Well, we have a higher Z effective. We also get, so we have more, we'll get more energy out of it. We have more attractive forces. So we get more energy out of it. As we go down a periodic table, there is a gradual decrease in electron affinity. Now, this is only a gradual decrease as opposed to a large decrease because of 2 opposing factors. Even though Z effective is not really going up, the added atomic radii means there's less electron repulsion. When there's less electron repulsion, we can fit the electrons in that much easier. We can fit the electrons in that much easier, and so we're not losing any energy to fighting the negative repulsion. And so we see there are a bunch of exceptions to these guys that buck the trend. And this is due to there's different jumps between the subshells, and there's different jumps based on the pairing of electrons. And there's a special energy stabilization that comes from being half filled or fully filled subshell. So if you look at, say, for example, nitrogen, the center of the P has like 0 electron affinity. 0 electron affinity. Boron is negative 27. Carbon is like negative 12,121. Oxygen is negative 141. Fluorine is negative like what, 320 or something. Neon is 0. Nitrogen is 0. Well, neon is 0 because it has a filled subshell. We don't want to add any electrons. If we added any electrons to neon, we would start filling in the 3s orbital. It's happy with a filled subshell. It doesn't want to add any more. Nitrogen doesn't want to add any more because it has 3 unpaired electrons. And so when we add another electron, you would have to pair them up. And so that adds some electron repulsion that just makes that a little bit less stable. And so you might see some trends in here that some weirdness. And the weirdness is basically explained by these things that we're not going to worry about too much. I'm not going to try to call you on these weird like exceptions. But just know there are these exceptions present. You can kind of see it here, the ionization energies. As we move across the table, and jumps down, and you have points where it jumps up, jumps down, then continues back up. That has to do with the energy it takes to remove from the P versus the energy it takes to remove from the S, or the energy it takes to unpair an electron versus take out an unpaired electron. And so there are some weird trends in there. You can look at them. If they come up, I want you to be like, oh, he did talk about this briefly, but I'm not looking to try to trip anyone up on these. If it comes up on homework, I don't want to be like, well, we never went over this. Well, I just want you to be familiar. There are some weird trends, but we can deal with them. Okay. So the last thing we need to talk about is ionic bonding. So what is this actually occurring? So the metals and the nonmetals are going to form a bond. This bond is going to be through an electron transfer to form a cation and an anion. These cation-anion pairs are held together by electrostatic attractions, the opposite charge. Basically, when a cation loses an electron to become positive, it's like becoming a positive pole of the magnet. The anion gains an electron, negative pole of the magnet, and then these guys can act like north pole, south pole of the magnet and start attracting each other together. Now, typically, when we deal with these, the electron came from the cation and went to the anion. It's not like free floating out there. It's usually electron transfer. As we do this, like depending on how many electrons we have to lose, we might be losing them from, like, say, having a bunch of different bindings together. As an example of like aluminum has to lose 3 electrons, and so each chlorine will gain 1 electron. But the one thing is to note is the ions will tend to adapt a noble gas electron configuration. Sodium, by losing 1 electron, it adopts the noble gas configuration of neon. It has gone from 1s2, 2s2, 2p6, 3s1 to 1s2, 2s2, 2p6. Chlorine, by absorbing an electron, it's become like argon. 1s2, 2s2, 2p6, 3s2, 3p5 is now gone to 3p6. They've both adopted a noble gas electron configuration. They're most stable, and then they're held together by the ionic attraction. But one of the things we had to deal with is these guys are not just a single pair. We may write them out as a single pair, but they are not a single pair. They're rather a million trillion ions generating a large crystalline lattice structure. We describe this as a single pair because we're describing the formula unit, essentially the empirical formula of this structure. If we tried to name the whole thing, we'd be here forever. Is this like Na 5 million, Cl 5 million? I don't know. But it simplifies to NaCl. We cannot just get this into one simple molecule. So we're going to deal with this. These crystal structures do not always adopt a simple packing. They adopt a repeating structure that isolates each cation to the anion. So this is the crystal structure of sodium chloride. So I want you to look. Each green is the chlorine. Each white is the sodium. We look here, the sodium here is surrounded on all 6 sides by chlorine. Chlorine, chlorine, front and back, left and right, down and up. Each chlorine is surrounded by a sodium, left and right, front and back, down and up. And I know I've ended the structure here, but if I keep going, there's going to be a positive on the front of this. There's going to be a positive above this chlorine. And that's going to keep repeating until we get to the very edge of that crystal structure. It's got to end somewhere, but the idea is that you have this repeating pattern of where these packing together, so you keep the positive and negative apart. And this happens in every single ionic compound. Every single ionic compound, we're going to have a crystal structure somewhat like this. Maybe not as nicely packed as this one, but there's going to be some sort of repeating structure. And when we get to solids next semester, we'll look some more at these repeating structures. Just know that this repeating structure is going to be the main part of all ionic compounds. Now, there's something special about here. If we calculated the amount of energy to produce this, we notice something weird happens. If we take our starting point of M, if we say, how much energy would it take to make sodium chloride from 1 mole of the metal solid and a half mole of the chlorine gas? And try to calculate that. If we calculate that by all the numbers we know, there's sublimation, that costs energy. Ionization energy costs energy. Breaking the bonds of the diatomic gas, that costs energy. Then we add in the electron affinity. We've only gone here. So far, there has been, from here to there has been almost all cost, no benefit. Almost all cost, no benefit. But to get from here to there, which is where the product actually is, we get a huge boost back the lattice energy. When we stick these two magnets together, these positive and negative together, we get a huge boost, which is the lattice energy. Energy it takes that we get from weaving these positive negatives together. This is stronger than every other cost. And it's why these guys will actually form. The lattice energy is so strong that it makes the formation of solid into a highly exothermic process, meaning it produces a lot of heat. You mix these together, it's going to produce a lot of heat, sometimes going to cause some explosions. So now this will depend on how well the ions pack and how well the attraction is. You will not need to use this actual equation right here, but typically you can make a broad sweeping generalization about this. And there is one question on the homework about this, that basically the energy is equal to a constant. You don't need to know it. The charge as a whole integer value of each ion, and D is the bond distance between them. So as the charge increases, lattice energy increases greatly. So NaCl would be 1 times 1, because plus 1 and minus 1. If I went instead MgCl2, that's going to be 2 times 1. If I said Na2O, that would be 1 times 2, because we have a -2, +1. And if I said, say, MgO, like we did in lab, that would be a 2 times a 2. So we see 1 times 1, you're going to get 1 times kappa. 2 times 1, you're going to have 2 kappa. 2 times 2, you're going to have 4 kappa. You're seeing a big jump as you go up in charge. Size is only going to increase a little bit, but as the size goes up, elements get farther apart, and thus there's less attraction. Remember, magnetism decreases as you move the magnets farther away. So as the elements get bigger, they get smaller. So what does that mean? What does that mean, the distance, in terms of this? If I compared NaCl with KCl, what have we changed? Na is still +1, K is still +1, but the only thing we've changed is K is now bigger. K is now bigger than Na. So size has gone up, so lattice energy would go down. The denominator increased, and so the resulting number becomes smaller by a bit. If I then went rubidium chloride, RbCl, rubidium is bigger than potassium, so the lattice energy would go down further. And so the generalized trend is bigger size, lower energy, bigger charge, much bigger energy. And so you could empirically compare these guys. And that is one question on the homework. That is all this chapter entails. It's a short chapter, very short chapter. I'm going to see if I have enough time, if I can pull up Achieve real quick. But starting like Tuesday or Wednesday, not Tuesday, starting Wednesday, we will start looking at last year's tests. I've posted them up. They are there. We will look at the test is going to be probably middle of next week. Like, I'm going to do the same thing with the test again. And we do on a weekend. We'll start the next chapter well before the test is due. But these chapters 4 and 5 are what's going to be on the test. We are well ahead of where we need to be. Chapter 4 homework, some of that stuff is due this weekend. Chapter 5 homework and all of the Chapter 4 assessments due is going to be due the same weekend of the test. So you have some chance to work ahead in the homework. Don't waste that time. If this stuff is struggling with you, if you're struggling with it, get some help. You'll have some time to get some help before this will come up. Okay, let's see. I'm pulling this up right now. Oh, okay. Okay. There's this assignment for Chapter 5 really isn't that long. Learning curve. Oh, there we go. So let's look at this. Clear tips. So it's like, I'd like to say 10 or 11 problems. Not really long because it's not a really long chapter. But here they ask us to recognize for the following elements the core electron count and the valence electron count. Core electron count and the valence electron count. So remember, The core electrons are every electron before the last row it's on. So neon would have 2 core electrons, and it would have 8 valence electrons. The S and the P would be those. So bromine might be a little tricky. It might mark it wrong because technically the D electrons would fall under the D electrons would fall under its, but it might consider those as part of the core. Because we're really only going to lose from the S and the P, not really from the D group in the periodic table. But so the bromine might throw a little issue. But okay, let's see. This one, put them in order of increasing radius size. So you're asking to put the trends there of these neutral atoms based on where they show up on the periodic table. You can, I think the hint probably will go to the chart. Ask you to put radius size of different charged atoms of one type. So you're just comparing cesium plus and cesium or calcium. Doesn't really matter, but the different charged ions of that. Ionization energy trend. This one, based on this ionization energy chart, what group does this belong to? We'll look at this a little bit more. Is that electron affinity? Let's see. Yeah, so there's a few ionic energy. Like, so give the element of this. Like, see, I'm trying to find where is the ionic energy one. Oh, based on the ratio of this to that, what is the likely element? If this is a 1-to-1, if this is a 2 minus, and that must be a 2 plus, what element must it be? Oh, it could be beryllium, magnesium, calcium. And then here's the last. Put these in order of ionization energy. So the first order you want to put this in is the charge. Figure out the charge of everything and then put them together. If this is 1 and 1 and 1 and 1 and 1 and 1, then they're all, you have to compare them by size. But if this is 2 and 1 and there's another 2 and 1, then you compare them by size. If there's a 2 and a 2, that's going to be the largest energy. And then you're going to compare the 2s and the 2s, the 2 and the 1s, and then you can compare the 1 and the 1. So you want to look at charge first, size second. Charge first, size second. But this is an example of, we don't need to put a number there. We're just looking at a general trend. And a lot of these chapter is general trend, not a whole lot of actual math. But that's where we're going to stop for today.